Okay, moving along, we're going to talk about phosphorus fertilizer now. This is an important component in terms of phosphorus management, of course, and uh, it's a little bit similar to nitrogen, where we talked about ammonia being the kind of the primary feedstock for really all nitrogen fertilizers. Rock phosphate is just that analog for phosphorus. So rock phosphate is a primary raw material that is really the formation of all phosphorus fertilizers. Um, as it exists, it's not water soluble, so it has to be essentially processed, ground, and then acidified to make more water soluble. From a kind of a geopolitical perspective, it's a little bit shocking or an interesting point to note that 72% of all the phosphorus mined comes from just a few places, a few countries. Morocco is sitting on really the world's largest source of phosphorus mine. There's China, U.S. produces roughly 20% of phosphorus worldwide, and then Russia, Belarus, or some other places. So there's some, minerals or, things like lime, which is essentially just calcium carbonate that they dig out of the earth and they mine and they crush up. And it's ready to go, right? But phosphorus is a different beast. It actually takes quite a bit of refinement that happens. In a very generic sense, it's really ground and acidified, but there's a lot more to it than that. We're not going to get into those details, but if you ever have an opportunity, say, to tour a phosphorus mine or to kind of learn more about it, it's pretty interesting and very energy-intensive process in terms of this, but it's highly, highly important from an ag perspective. Global fertilizer use, you can see from the 1800s to 2000s how much phosphorus fertilizer was used, right? And so we've got manure, human excrement, guano, or bat droppings from caves, and this rock phosphate. And like many things, this is a graph for phosphorus, but like many things, this is a common thing that happens in the 1950s with the kind of industrialization of agriculture. We see huge increases in actual use and demand, and so phosphorus not being any different in this regard. We can think about worldwide versus U.S. use for phosphorus. Okay, so we the last, say, 20 odd years, maybe 30 years, we've seen a constant increase in these dark squares, MAP and DAP. Those are our two primary phosphorus fertilizers. Monoammonium and diammonium phosphate. There's SSP, single superphosphate. That's very common still in some parts of the world. Triple superphosphate, and then other phosphorus sources. Okay, so you can see worldwide it's really single superphosphate and these ammonium phosphates that dominate the market. For the United States, it's DAP, it's AAP, ammonium polyphosphate, and then MAP has really increased and is about to become, the most popular fertilizer in the U.S. Things like triple super and single super, we can see triple superphosphate, TSP, and single super have really declined over the last, say, 20, 30 years. Okay, and to the point now where triple superphosphate used to be a very common fertilizer that we would use in experiments. It's very, very difficult to find here in Ohio. I don't know of anyone that sells it. We have to have it trucked in if we want to use that form of phosphorus from other parts. It's becoming a rare commodity. So, P fertilizers can broadly be classified into a few main categories: calcium phosphates, ammonium phosphates, and potassium phosphates. And so, here's again from a table from a Haviland textbook, but we've got rock phosphate as the raw material, and this can certainly be used. It's just not much of it. 20% at best is available, so you can apply it, but you're not going to see a lot of that in terms of availability. Single super and triple super is calcium phosphates. Much better availability, 80, 90% or greater availability. But then we get into these ammonium phosphates, which really are just much more available, and it's really they dominate kind of the marketplace. Somewhat because of that, somewhat for other reasons as well. Okay. So phosphorus fertilizer, obnoxiously, it's in this phosphorus pentoxide, this P2O5. Okay, and that is this represented, by this magical diagram that really doesn't exist in nature, but for whatever reason, the industry has used this historically as kind of like the standard metric for phosphorus fertilizer. So it's important when we're thinking about, talking about phosphorus, to think about either elemental P, which is just P by itself, versus P2O5, which is 2 P's and then 5 oxygens. So when we're talking about P2O5, there's actually less phosphorus in it. It's a more dilute form. And so we have to be careful about that. And when we see fertilizer of, 1034O, for example, that 10-34-0, that 34 is not 34% phosphorus, it's 34% P2O5. So the actual elemental P concentration is even less than that. Plants really don't take up phosphorus pentoxide. Again, they take up these orthophosphates like we've already discussed. Tri-state fertilizer recommendations are in line with the fertilizer industry. We haven't talked about the tri-states. These are the Ohio field crop recs, and we'll get into those in a few weeks, do a deep dive into that. But the recommendations are in P2O5, but soil test labs can report results in phosphorus in pounds per acre. So there's just, we just need to understand some of the nuance here and be aware of it so we're not, mixing some of these things up. Converting from P2O5 to elemental phosphorus, we need to divide by 2.3. And going the other way from elemental to P2O5, we're going to multiply by 2.3. Okay, so really, when we, that's not trivial, right? It's like if we're talking about elemental P versus P2O5, it's elemental P is almost 2.5 times more concentrated form of phosphorus than P2O5. So it's something that we need to be aware of. Most common P sources, MAP and DAP, as monoammonium phosphate and diammonium phosphate. Both are made by reacting sulfur with rock phosphate, so this sulfuric acid. And then we also form this ammonium compound, okay? So, or we add this NH3 to it. So it's either a monoammonium, so one ammonium, or a diammonium, 2 ammoniums. And you can see the chemical right here. These are both MAP and DAP are water soluble. They're dry granular fertilizers, and so they can be directly applied. They can be blended with other fertilizers and like bulk blended. They've got a very high concentration of nutrients. 52 for MAP and 46 for DAP. So roughly half of that fertilizer is P2O5. It's not half is elemental phosphorus, but half is P2O5, and we can zip back here and see this right here. Typically, the common forms that we sell that we typically see would be 1152O, and for DAP it'd be 1846O. That would be the most common iterations that we'd see. And applying P with ammonium can be advantageous because we often will see a complementarity with the nitrogen and the phosphorus in terms of stimulating root uptake and stimulating that phosphorus uptake. So, there's kind of a synergy in this ammonium phosphate versus the calcium phosphate or the potassium phosphate. Okay. DAP is the world's most widely used fertilizer, sold often as 1846O. The initial reaction is basic, so the initial reaction around that granular drives the soil to a pH of about 8.5. It depends on where you start from, of course. Because of this, it forms free ammonia, and that can be toxic to seeds. And so we typically do not recommend DAP as a starter fertilizer. DAP is almost always broadcast applied. And because of that, a lot of people are using MAP more often and just using it as kind of a more forgiving or more universal fertilizer. Okay, so for DAP, we do not recommend it as a starter fertilizer. We do not recommend you ban it. Nitrification of this ammonium will eventually occur, and that will acidify the soil. So this pH will drop over time, maybe after a week or two. But when it's placed close in contact with a seed, it can be trouble. So we don't recommend that. For MAP, it's fine for starter fertilizer, and so we don't really. It doesn't pose a huge risk of seed injury unless you're applying at really high rates, and that. Anytime we're applying a high salt fertilizer with ammonium in it, we can cause seed damage. So we've got to be careful with that. So commonly sold as 1152O, 11% nitrogen, and then 52% P2O5. It's a slightly acidic fertilizer. Okay. Moving on, it's ammonium polyphosphate, APP, most commonly in the industry referred to as 1034O. There's some iterations. There might be an 1137O, etc. But 1034O as ammonium polyphosphate is the most common liquid phosphorus fertilizer. So liquid solution easily combines with other liquid fertilizers, things like 28 or UAN, right? These are fertilizers that will be very common as kind of a starter fertilizer mix, and you can control the relative rate of nitrogen and phosphorus by how much 1034O you use versus, say, 28 UAN, right? It handles and stores easily. It's easy to apply or whatever. It's not it doesn't require special equipment, et cetera, et cetera. So it's considered very effective, just as effective as MAP or DAP. MAP in terms of a starter context, but MAP or DAP from a broad perspective. 1034O, because it's got water, typically is applied most commonly as a starter fertilizer. That is when the plant is planted. I'm talking about field crops here. But it can be applied in a number of different contexts. We can apply it with micronutrients, et cetera, et cetera. It can be banded on the surface. There's a lot of different ways people actually use this fertilizer. Okay, there's calcium phosphates. No real change in pH effect. They used to be very common, but they're not very common anymore. These things like single superphosphate and triple super, which we just mentioned. So it's phosphate associated with calcium. They were really the first kind of commercial pea fertilizer out there, and but again, the use has diminished over time. Okay, triple superphosphate was the most common calcium phosphate at 046O. I mentioned this just a second ago, but we really like this as when we're doing fertility trials because it's nothing but phosphorus, right? There's no nitrogen in here. And so that way we don't have to worry about if we see an improvement or a detriment, is that from the from the phosphorus or is that from the nitrogen? Okay. This would be a triple super phosphate, and single super are dry granulars. Have been used widely but difficult to find now. So potassium phosphates, we don't see those in kind of the agronomic field, but in the hort industry, we might, with crops, things like tomatoes or potatoes with high levels of K removal, we might see this. But oftentimes, depending on where you're at, what you're growing, it's often cheaper just to buy phosphorus fertilizer by itself and then potassium fertilizer and blend them. But in some cases, it makes sense to buy them as potassium phosphates, but again, these are typically more expensive and as a result harder to find or just more specialty application. All right, so for fertilizer P reactions, we apply fertilizer. Then what happens? Well, there can be a number of a number of possibilities, of course. But so first, it's either adsorbed, precipitates, immobilizes, or diffuses, right? And so, just as an example, looking at something like triple superphosphate and the various weeks, 1 week, 2 week, 3 weeks. Here's the total extractable P levels, and then here's the relative native soil phosphorus level. Okay, and so we can see when phosphorus levels are very low, that are after 1 week we have high availability, and then that drops. But when phosphorus levels are very high, or as the native soil P level increases essentially, then it's got a less of an effect in terms of on a weekly basis, and it will not have such a kind of difference between the 1 and the 4 weeks when the levels increase. Okay, so the influence of soil type on residual P availability. So these are related to a lot of the concepts we talked about P fixation in the last talk. Calcareous soils, slightly weathered, moderately weathered, and highly weathered soils. And so we can see when we apply how much P is available after 6 months time, and that just showing that different soils react differently and either are more available or less available over time. Okay, so the ranges can be tremendously different depending on the soil, but if we look at the means, slightly weathered soil, maybe six months later, 50% of that fertilizer is still available, and as soils weather to moderately highly, we get essentially a half reduction in terms of P availability. In other words, fixation rates going from 47 to 27%. Really, this is availability, but our P fixation rates really increase. So highly weathered soil, only roughly 25% of that fertilizer is still around after 6 months. Okay, so just important to know about this. Ortho versus polyphosphate. This is kind of a perennial issue that we run into phosphorus fertilizers. So there's orthophosphates, and there's which are a single molecule. Then there's polyphosphates, which are essentially more than one of these orthos linked together. You'll hear all kinds of stuff from fertilizer sales reps talking about, oh, well, you need an ortho because the poly can be bound up and it's not available. And it's really not. It's an unfortunate urban legend that exists, but it's really not true. Maybe in some very rare cases, but typically when we apply poly or orthophosphate in soil, the polyphosphate is going to disassociate and break down into orthoforms very quickly. And so there's really no real advantage between ortho or poly, despite what a fertilizer salesperson is going to be telling you. The one main difference that does exist is that polyphosphates are able to chelate some micronutrients, things like zinc, which could be an important source of zinc nutrition. And so it's just something to keep in mind. But typically the ortho versus poly debate is kind of a silly one that still exists, and it's be kind of skeptical when you hear somebody spouting the differences between these two. We know that our phosphorus fertilizers that we just talked about are very soluble, very readily available, regardless if they're in the ortho or the poly form. Okay, organic P fertilizer sources. So again, generically, there's a lot of organic waste that make excellent sources of P. Manure, biosolids, compost, rock phosphate from a certified organic perspective, and then of course there's always P coming from the weathering of soil. So these are all potential P sources. Concentrations of comes at no surprise. Concentration of P in organic amendments differ, and so that's why when we're applying manure or applying some kind of organic amendment compost or whatever it might be, getting a nutrient analysis to know what you're applying is very important. Here's total P versus organic P depending on different types of manures or compost, and you can see the differences that do exist. And the forms exist too, so it's not just the total versus inorganic, but it's or the total P, but it's the type of P. And so we've got these total inorganic and organic, and then in solution microbial P, et cetera, et cetera. So it's not just how much phosphorus in that material, but then the form of that material, and in lots of ways that has to do with the availability of phosphorus, and sometimes we get at that availability by doing these kind of successive fractionations and looking at how available or how unavailable phosphorus might be in a material or in the soil. Organic P amendments are a really good source of nutrients. They're often cheaper. Typically we're adding organic matter, and it contains often micronutrients, plenty of other things besides just phosphorus. So there's a lot of advantages of using and recycling organic P, right? Everyone gets that, but some of the disadvantages, of course, cost of transport, the variability in the source. So it might be swine manure, but we might not exactly know how much is, well, we might be able to quantify how much is in there, but having a really good estimate of how much is available is a different story, okay? So estimating plant availability can be tricky. And then one of the biggest drawbacks is this imbalance of nutrients, okay? So we know when we're adding P fertilizer, and we'll spend some more time talking about this next week, but when we're adding P organic fertilizer, say as manure, for example, that manure pit, through gaseous losses of nitrogen, volatilization, denitrification, might be losing a lot of N out of that manure. So what happens is over time, manure nitrogen goes down, but manure phosphorus stays the same. And then what's a typical practice, or what has been typically done before people got more sophisticated about nutrient management, is that you just go out and you apply manure at whatever rate you need a nitrogen. So if you're a dairy farmer, you're just going to go apply manure to, say, ahead of your corn crop, and then you apply how much manure that, in terms of the units N that you need for nitrogen. Well, when you do that over time, because phosphorus levels are higher, we get phosphorus building in soils. And this is a major problem with honestly, most livestock operations in the state, and it's not just Ohio, it's lots and lots of places where we have a large concentration of nutrients in animals in a confined feeding operation, whether it be a dairy or swine or whatever it might be, chicken, and we bring a bunch of grain or a bunch of nutrients in to feed those animals. The cost of the transporting that manure and disposing it on land becomes very large, and often those farms or those soils can get a lot of phosphorus, much more phosphorus than they need, and we get phosphorus loading events and soils with really elevated phosphorus levels, and that is problematic for phosphorus loss. And that's, we'll talk more about that next week, but when we have higher phosphorus loaded soils, those are soils that are really going to be losing phosphorus at higher rates, okay? So land use history is a big part of soil phosphorus, and legacy phosphorus, as we talk about this, when we might have soils in the state that haven't had phosphorus applied, fertilizer phosphorus applied, or any phosphorus for that matter, for 20 years. And we still might have levels that are very high, into the several hundred parts per million. But these are soils that historically had lots of phosphorus applied, typically as manure, and then those levels really elevated. and that can last for a long time. It just doesn't go away. Like, if we went out and dumped 1,000 pounds of nitrogen, that would have real effects, but maybe after 10 years, you might not be able to detect that anymore. In phosphorus, it sticks around. And so, showing this is just a graph over depth, and then soil test P, again, a measurement of P availability, and different levels of fertilizer are applied of 40 pounds of P per acre, 90, and 110 per acre per year over 10 years, and you can see what happens. Now, when we're growing crops, we're typically anywhere below 50 part per million. So these would all be soils that would be very highly phosphorus loaded, and that would be considered nutrient imbalance, right? So we want to avoid that situation when we can. All right, so that's phosphorus fertilizer, and we'll end this week's phosphorus next time with wrap some of this discussion up with phosphorus fertilizer management considerations.